Topic 4.9, reduction of a simple distributed loading. This is the last topic from chapter 4. Reduction of a simple distributed loading. Today's objective is to determine an equivalent force system of a distributed load. Until now, anytime when we have force acting on system, we have drawn that force as by single arrow, like F, and like we have drawn the arrow acting at one point. So this type of load is called point load. However, in real life, the load is not always a point load. It does not act at one point, but it actually acts over a length, or over an area, and that type of load is called distributed load. For example, all this like wooden plates here, they apply the load not at one point, but they apply the load uniformly over the entire area, and that type of load is called distributed load. And in this section of the video, we will learn how to convert this distributed load into a point load. The resultant force Fr due to a distributed load is equivalent to the blank under the distributed loading curve. It's equivalent to the area under the distribution. So this is how graphically we represent the distributed load, and this x-axis is the position and y-axis is the value of load. So load here is in terms of like Newton per meter or pound per foot, depending on the unit system. So it's not Newton anymore, it's per length. So load is per length. Now this distribution indicates the how the load is distributed over the area. So if it is a straight line, then that type of distribution is called uniform distribution. Or if it is like this, then that distribution is non-uniform distribution. And to find the equivalent point load, we need to find the area under this distribution, which is Newton meter multiplied by length meter gives us the Newton as the final unit. Okay, so it's the area under the distribution. The line of action of the distributed load's equivalent force passes through the blank of the distributed load, and the answer is centroid of the distributed load. We will learn that during the presentation. Applications. There is a bundle of boards stored on a storage rack. This lumber places a distributed load due to weight of the wood on the beams holding the bunk. To analyze the load's effect on the steel beams, it is often helpful to reduce the distributed load to a single force. How can we reduce everything to like just one force? And that's where we need to apply the distribution equations. Another application is the wind applies the pressure on this triangular signboard. That wind is applied over an area. Now, when we design the signboard or they design the strength for this vertical column here, we would like to know the equivalent point load of this distribution. So to be able to design the joint between the sign and the signpost, we need to determine the single equivalent resultant force and its location. Look at this fish tank. How much force is applied on the bottom of the fish tank because of this water? So water does not apply point load, but it applies the load over an entire area. So that's the distributed load, and we need to reduce that into a point load and determine the exact location of the point load while we design the such system. Now let's take this example that this is how the load is being distributed, where x-axis indicates the distance and w indicates the value of load. And the distribution is not uniform. It follows this mathematical function here, where w is function of x. Okay. Now, in order to calculate the equivalent point load, we need to consider an element of length dx. So consider this small rectangular strip which has the size dx, length dx, and its height is given by this equation wx. So the point load for that system is wx multiplied by dx. But to find for that's only one strip. But how do we find the total equivalent point load for the entire distribution? We need to do the integration of this small strip over the entire length. That means we just divide the whole thing into series of these vertical strips and add them together. Now instead of doing that, we just do the integration. So the net force on the beam can be calculated using integral of df, this small strip, which is integral over the length Wx dx. And that's nothing but the area under this distribution. So that gives us the point load, equivalent point load. But now the next question is, where would this point load act relative to point O? So x bar is the location of the resultant load relative to point O. To find that, we need to apply the concept of equivalent force system using moments. So the net moment of the distribution about point O should be same as the net moment of a single resultant force about point O. And that's what we do here. So the net moment of dF about point O can be calculated using x time dF, and the total moment about point O because of the distribution is x multiplied by dx multiplied by dx. So previously we had wx dx only, now we have x because this is like force multiplied by distance, that gives us the moment. Okay. And for the equivalent diagram, we apply the same concept and we calculate the resultant moment, which is Fr multiplied by x bar, where Fr itself is integral of distribution over the length. So these two moments are same because they both are coming from the same load. One is distributed load and second is equivalent point load. So we can equate this part with this part. And when we do that, we get this final equation, which helps us to determine the location of x bar. So location of x bar is moment divided by resultant force. It's x dA divided by dA over the area. And we will solve some problems using this equation through our in-class exercise. Now, a couple of distribution examples. So in this case, the load distributed load is given as 400 pound per foot. It's applied over 10-foot distance or 10-foot length. So equivalent point load is 400 multiplied by 10. It's nothing but the area of under the rectangle, which is length multiplied by height. So that is 4,000 pound. And now to find the exact location of that, we need to apply the moment equation such that the moment of this distribution about this point should be same as moment of this force about point O. If the distribution is triangular, then area under the triangle can be calculated as 1/2 times base times height. So where this is base of the triangle and this is height of the triangle, and using that equation we can calculate the distributed load as 1800 Newton based on the given information. Okay, and we can pinpoint that load exactly at one fixed location using the moment equation. So the moment, so 4,000, so this entire distribution can be replaced by one force. This triangular distribution can be replaced by one force. And that's what we are going to do through our in-class exercises.